Today I'll talk about the crystallization of a transition metal oxide in aqueous solution studied using in-situ XAFS. My name is Sang-Wook, collaborators Dr. Eun-Seok Jeong and Dr. In-Hee Hwang at Jeonbuk National University in South Korea. Today I want to show that growth mechanism of zinc oxide. In 2001, Dr. Rainer Bissell has showed that zinc oxide nanorod and the zinc oxide nanotube can be fabricated by using aqueous solution method. After that, many people has reported the fabrication of zinc oxide transition metal oxide nanostructures by using aqueous solutions. This is just some example of that transition metal oxide nanostructures fabricated by using aqueous solutions like TiO2, Mn3O4, CuO, zinc oxide, CO3O4, nickel oxide, P2O3, and others. However, the crystallization mechanism of transition metal oxide at initial stage is still unclear. So we're using the XAFS measurement to understand the growth mechanism of transition metal oxide. We started with the zinc NO3 powder to understand the zinc oxide growth. So we put in this powder into water, and we applied HMT at room temperature. HMT is the C6H12M4, which is reactive with the water and generate the NH3 ammonia. And when the ammonia reacts with the water, then it generates OH minus. So when we put in the HMT to the water, then the concentration of OH is increased. So this pH level shows that OH is generated by the HMT. So this is what we call the A sample, this is what we call the B sample. After we apply the HMT and we heating up the solution to 60 Celsius C, and then we measure the XAFS, we call this temperature C. And then about 6 hours later, we found that some precipitate in the bottom of the beaker, and we take the sample from the solution, and also we take the precipitate from this stage. And also we got the sample after heating up the 80 Celsius C, and we found the powder from the solution. And we dried the solution, and we got the zinc oxide nanos. So we had 1, 2, 3, 4, 5, 6, 7 samples, and we measured it. So this is a SEM from that zinc oxide precipitate stage, which at about 6 hours later at 60 Celsius C. SEM images show that there are two different structures. One is the nanostructure, rod shape, and the other one is the round shape. We know that this round shape is the zinc O complex, which is not fully formed into crystal structure, but this non-rod structure is the zinc oxide. So basically, this precipitate has the mixed phase of zinc oxide and the zinc O complex. When we heating up to 80 Celsius C, then we got the precipitate, which is different from this one. And this sample is called zinc O nano. And we measured the XRD from this sample, and we had a very good XRD patterns. We fit this XRD to the zinc oxide crystal structure, and we found that most of the zinc nano sample has the zinc oxide structure without any extra pH. We measured the XAFS at the zinc KH at different stage. This is initial stage. This is we applied HMT and heating up, something like that. And during the zinc oxide growth, white line is been changed. But the absorption H line is not changed very much. That means the zinc oxide keep the 2 pulse chemical balance state during the zinc oxide growth. Here, the black line is the sample of the zinc oxide powder. So this is basically the zinc pool, the standard of the zinc oxide. After we remove that atomic background, we got the zinc oxide XAFS data. This is we got from here. After we got the XAFS signal, and we transform to R space. So this is a XAFS data which measured from the zinc oxide growth stage, and this is initial stage. This is when we apply HMT. This is we apply heat on there, and you can see that is initial data only zinc O pairs. Later on, the zinc pairs show up. In order to get the quantitative local structure property, we fit XAFS data to the XAFS theory. This is some representative fit result, fit of the zinc oxide data. So here the open circle is correspond to the fit, and the solid line is data. So this data is correspond to this one, and this is data is to this one. So from the XAFS fit, we get the quantitative information of the local structures. Zinc oxide has the 4 coordinations of oxygen as a first neighbor, and 12 coordination of zinc as a second neighbor. Zinc oxide solution show that there are only about 3 oxygen coordinations without any zinc coordinations. When we apply the HMT, then the zinc coordination is show, but they are very unstable. When we heating up, then it becomes really more stable. And at the precipitate stage, you can see that the coordination number is increased. And then at the zinc oxide nanostructure case, that local structure around the zinc is quite similar to the zinc oxide powder. It shows that it's around the 4 coordination of the oxygen and about 12 coordination of the zinc. The XAFS provides only the local structure property around the zinc atom, but does not give that information of the structure of a zinc O complex. Furthermore, XAFS cannot detect the H ions binding to the O oxygen ions, although OH play a critical role in the zinc oxide crystallization in solution. So we performed the semi-empirical quantum chemistry simulations based on the XAFS result to obtain the structure of a zinc oxide complex. This is just some example of that simulation of the SEQC, and zinc molecules come together, then they bind each other by reducing the energy and form this kind of structure. And OH is react with this zinc complex, then it also reduces that total energy, and OH bound to the zinc atoms. Based on this simulation, we obtained that plausible structure of the zinc complex. In the zinc oxide solution, we expected about there are 5 plausible structure in the solution. And when we apply the HMT, then there are 4 plausible structures expected by the SEQC simulations. And when we heating up to 80 Celsius, 60 Celsius, then we expected that there are about 3 plausible zinc O complex structures. Although there are different structures, but we compare to the XAFS result and also the stability of that structure, we expected is probably this B1 and A1 is more stable than the other structures. In the solution at the 60 Celsius C, after 6 hours in the solution, the zinc complex become like this kind of structure, and the precipitate of the zinc oxide at the bottom of the solution become like different structure. So this structure finally change to that zinc oxide. So based on the XAFS, measurement and SEQC simulations, we finally found that initially the zinc oxide complex has a this structure. When you apply HMT, then the complex change to this structure. And then when you're heating up the sample above 60 Celsius, then this change to this structure. Once zinc complex has this structure, then they immediately change to or form into the zinc oxide. So this is a seed of the zinc oxide that we found from this study. So we noticed that the OH created by HMT play a critical role in zinc oxide crystallizations. Above 60 Celsius, the seed of zinc oxide, which formula is here, 6 zinc OH2, is formed in zinc complex solutions. Once this seed is formed in the solution, they agglomerate and become large clusters. Chemical energy and the energy minimization are the most important factors in crystallization at the very initial stage of crystal growth. Thank you very much for your attention.